Hello, everybody. So this is the second lecture that we have this week because I grouped together the roof lecture and then the thermal and moisture protection because I just think it makes sense to put those two together. Roofs protect us from the elements, and so does our thermal and moisture protection that we include in our building envelope, which is the surfaces that we use to protect us from the outside. So the envelope would be the roof or ceiling, the walls and the floors that surround us and that are insulating us from the outsides. So here is just like an introduction to it right here. So a good building envelope system, which includes the roof, the walls, the floors, ceilings in some cases, protect us from all those elements. And this is a good illustration of how the rain runs off the roof, and with a good overhang we can make sure that the rainwater doesn't hit our wall. And then our walls themselves have horizontal siding or shingles, and usually have something that's called a rain screen behind that makes sure that the moisture doesn't get into the wall system. So that would be very bad. Moisture getting into the wall system and condensing there and creating mold is not a great thing. The other thing that we're going to be doing, so this is kind of the wet, damp, and cold, the wet, damp, and moisture stuff. This is the heat stuff here that we're illustrating. So this is representing the inside of the house. This is representing the outside of the house. And what we're always trying to do is keep the heat that we put inside the house, because we're in a colder climate. We are more concerned about making sure that our houses are good to heat and keep and retain that heat. So the inside temperature that we usually try to maintain inside a house is around 65 to 70 degrees. And then the house the heat system has to work to heat the house up and keep that heat when the temperatures get cold and drop outside. So what that's called, and that helps determine what kind of climate we're in, is called our heating degree days. And I kind of tried to explain it in layman's terms here. So in our climate, we're concerned with heating, and we're trying to heat our spaces inside to 65 to 70 degrees. In the summers, we don't have to do that. In the summers, the outside temperature is often warmer than this temperature, so we're not turning our heat on at all. So those would be days that would be representative 0 heating degree days. But as we approach fall, maybe in October, towards the end of October, maybe early November, we start to get uncomfortable on the inside of our house because the outside temperature is dropped maybe to around 40 degrees. And we want to keep inside of our house around 65 or 70. So the difference in temperature that we're looking at there, if this is 40 degrees on the outside and we're at 65 degrees that we want on the inside, desirable temperature, that's a 15-degree difference that we're 25-degree difference that we're trying to create between the two. So that is called the delta T. So that means the change in our temperature. Well, if you take into account how many times that happens over the year, and you add up all the number of degrees we have to heat out, the difference between inside and outside, it adds up to a pretty big number in our area, and those are called heating degree days. And so we're around 7,200. To give you an idea of what that means, like somewhere around North Carolina is around 4,500 to 5,000. And then if I go way up to Aroostook County or even more north, we might be closer to 8,000. And then in places like Antarctica, it's like 12,500. So in other words, we're heating most of the year. So that's how heating degree days work. And it's important for us to have some understanding of what that means. And it's the heating degree day number 2 is a good way for us to be able to put everybody on the same apples to apples comparison chart. So what we're trying to design is a building structure, an envelope that keeps our heat in and maintains it. So we have to use less heat to reach a temperature of 65 degrees inside when the temperature gets really, really cold on the outside. So this is our pretty typical construction that we've had for a long time. This is what it looks like in section, and this is what it looks like if it's broken out. So you have your studs that are placed at 16 or 24 inches on center. In between all the studs, we have insulation. On the inside of the house, we have gypsum wallboard. On the outside, we have a layer of sheathing, and then here they're showing a layer for an exterior air barrier membrane, and then they're showing an extra layer of insulation on the outside. These strips that are vertical are your rain shield or furring strips, and then the horizontal siding is placed onto those. So this is the pretty typical construction anatomy of a wall. It's actually improved from the original, which is usually we use batt insulation on the inside, which is very poor quality insulation. We didn't have the extra layer of insulation on the outside in the buildings we built in the 70s and 80s. And we put studs in some cases too close together. So it reduced the number of places that we could fill in insulation. And we'll see that everywhere we have a stud, basically think of that as a great conductor of cold from the outside, and that's where this extra layer of insulation is helping, because it's preventing that stud from getting cold from the outside and bringing that cold in. Older homes, if you've ever seen infrared studies done for older homes, you can actually see the studs. I'm actually going to see if I can do an infrared. See a house inspection and see if we can see some images of what happens. So this is a really good example right here. Everywhere you're seeing these colored images, you're showing that where the heat signature basically is on a house. This is a really good example. So this might be a house that was built you know, maybe in the 70s or 80s, and the insulation was put in, but all the insulation has fallen to the bottom of the wall. And so you can see by looking at it where the insulation is settled. And so that temperature is at 20 degrees, and it's at a higher temperature or lower temperature, depending on what kind of day it is. If it's a cold day, these colors change. If it's a hot day, the colors change in a different way. To show how much heat is either coming in or how much cold air is coming into the house. But this just illustrates, because you can see every stud, that those studs are conducting a lot of cold from inside to outside, and that's called thermal bridging. All right, so that's just kind of the anatomy and what, you know, why do we have all these layers in the wall and what are they doing? Okay. For a roof system, you have the layer of plywood sheathing down here, and then we have what's called felt paper, and it's laid in overlapping formats like this so that you can see that we're overlapping both widthwise and lengthwise, so that you're creating these pretty strong barriers between moisture and you know, any other kind of things, because these sheets are kind of overlapping each other and kind of adhered. At the bottom of the roof, at this section right here, which isn't being shown here, you will usually see what's called ice and water shield. Let me just do this to show you what that looks like. So this is a brand called Grace Ice and Water Shield, but what they're doing here is showing you how they're installing that ice and water shield at the bottom 3 feet of the roof. That's where ice dams can occur, so that's an extra layer, an added layer of protection that you're getting. We also might see that ice and water shield at the valleys of the roof, like you're seeing here, and at the ridges. This is illustrating ice and water shield covering the entire roof. I've heard from builders that that is not such a great idea because it's really, really difficult to remove it when it's time to replace or repair the roof. So the recommendation for code compliance is to put the ice and water shield at all seams. So that would be intersections between roofs, and then at 3 feet from the where your gutter or drip edge would be up the roof. and then it's not a bad idea to put one at the ridge, but allowing for a ridge vent if there is one. So that's what ice and water shield is. So this is a little bit older example of that felt paper, which the ice and water shield is a lot more like a membrane, and this is more like felt paper that's waterproof. And then this is how your shingles, these are called 3-tab or asphalt shingles, because you got 1, 2, 3 shingles, and a sheet can go down and you'll lay 3 shingles at a time. The first layer is always 2 layers of shingles. You can see there's 2 layers here, and then you start your coursing from there on. The reveal is the amount of shingle is exposed, or exposure is the amount of shingle exposed for each layer. And these are great for medium to high sloped roofs. And here's an example of thermal and moisture protection in your foundation system. So we've got insulation that is going from wherever, all this stuff is going to be backfilled here to backfilled against the foundation wall. And you can see insulation has been placed on the outside up to where grade will be. There would be some more insulation on the inside that will go up to where the floor would be most likely. And then this area here has all been painted with a waterproofing paint that protects the concrete from moisture. Because concrete's extremely porous, and so you've got to make sure you paint all the areas that are going to be exposed to the ground. Oh, let me back up a little bit. And let's take a look to see what the book has to say about thermal and moisture protection. So I'm just going to go to yeah, we'll run through this. So there's where I got the pictures from that you saw on the opening slide there. And let's go to wood shingles. And we're just going to run through a few of these things. So this is examples of the wood shingles, their rating and their length and their exposure, and their recommended pitches that you would put them on. And then it shows how the shingles are placed in the shingles, because these are wood shingles are placed one at a time. Takes a little bit longer, but it's a more attractive look in many ways. The other variation you can get that looks like this are composite shingles, and usually those can come in clusters because they're stamped out of a composite wood and plastic. And then what they're showing here too underneath this is, instead of sheathing, they're showing furring on top of the rafters to hang all of the shingles. Wood shakes, different than shingles in that there's hand split, straight shakes. I think that's the difference. A shingle can be made out of a few different materials too. So that's the difference. A wood shake, these are going to always be wood, and they have a distinctive look to them. They are popular in New England because a lot of them are cedar, and they don't need to be treated. They just, for the lack of a better word, they patina. They start off being that bright yellow or orangey color, and then eventually bleach to that kind of gray color that you get from the sun. Here are the composite shingles. So included in that category are the asphalt shingles, and we have 2-tab, 3-tab, random edge cut. You can see the shingles are changing, and then laminated overlay. And this shows you an illustration of how the shingles are overlapped, the width of the shingle, the exposure, and then the overlapping. And then just how some of the shingles are applied in difficult areas like valleys or ridges. Slate shingles are a really beautiful look, but they are a very, very, very heavy roof. So slate shingle cannot be applied to just any roof system. The roof system has to be designed to carry that load. It's a much higher dead load with slate shingles. Slate shingles are pretty much forever roofs because if a shingle falls off, you just go up, replace the shingle, and they last for a pretty long time. A lot of churches have slate shingles, and they last, because of how steep the steeples are and how steep the roof pitches are on roofs. They tend to be a good choice because they're difficult to maintain. There's a lot of scaffolding that needs to be done to fix and repair, and so slate shingles, because they last so long, are a really good choice. And then just different configurations. These are Spanish tile. And similar to a shingle, they last a pretty long time too. Just a single tile can be replaced. Really easy to maintain, but not great in the snow. They can deteriorate, crack, and in our area too, because we throw a lot of sand around in Maine, and we live by the ocean. These can deteriorate a little faster too. And then this shows some green roof construction. How does a green roof design work? And it's not really conducive for the Maine environment because we don't get enough growing season, so it makes it a little bit hard to keep a green roof alive. Corrugated metal is a very good roof system in this area. And you're seeing an example of how that's constructed. You have a furring system underneath, resting on top of the rafters, that raises that raised metal roof system, and usually the insulation and everything is below that. So this is almost like sits above the rafters with a big airspace, and the snow just sheds right off of that at the higher steeper slopes. Different just configurations for the pattern that we have here for the standing seam, and then what does the ridge cap look like? And then some examples of how those things are constructed and put together. So I did want to cover flat roof systems because they're really common in commercial construction. This one is pretty basic example of it. So you usually have a layer of concrete. It's on a concrete deck with that corrugated bottom. You have a layer of insulation that can sometimes be tapered if there are roof drains on the flat roof. And then you have a layer of the bituminous drainage stones at the top, on top of a continuous membrane that is protecting the roof system from any moisture. And when you do this kind of roof system, usually, especially this flat roofs often get like mechanical equipment put on top of it, and then paths need to be created for that mechanical equipment. And so they're showing here an example of how paths or routes that people are using to maintain that equipment will be designed into the roof system. So flat roof system on wood deck, flat roof system on metal deck, which is more common. And we have this, for instance, in our building at school. The Ross Tech building has this kind of roof system. And then we get into, our vapor barriers and moisture barriers. So this is the roof underlayment or felt, similar to what you have in a flat roof system, but this is showing many layers, with the final layer being that painted or stretched membrane, and then the bitumen or coal tar asphalt combination that creates a better drainage for a flat roof system. These are the slopes you should be using to drain water at a minimum 1 to 48. And then this is great for aggregate surfaces. 312 and 612 is good for smooth surfaces where it doesn't need to have the aggregate or the bituminous rock. And I'm just going to kind of fly through some of this stuff because it's mostly commercial applications and curbs, roof curbs, and get to the section on flashing. So roof flashing and penetrations. Flashing is done around areas that we create holes in our roof, and it's usually metal. and then maybe painted tar around it. And so this is an example of how flashing would be done around a chimney, it looks like, of some kind. These roof penetrations are for stacks from a bathroom. There's an example of that flashing. As soon as we penetrate or make a hole in the roof, we want to make sure nothing about that hole actually gets water in the wrong places. And I think we've gotten to the extent of what we want to see for thermal and moisture for most of the things here. Let me just see if it's going to cover wall systems we're getting into. All right, so yeah, this is now we're into plywood siding, and this shows you how the plywood siding can be applied to a wall system, and then different types of finishes that you can have: board and batten, reverse boarded batten, textured, and how you nail those pieces of plywood to your wall construction. So this is the reason for that spacing for those studs, is to have nailing points for that sheathing. And then your coursing for shingles, it's good to know, and different shingle shapes and types, and the way the shingles interlock with each other. So you got very different looks here. They look very different in elevation, and you see different texture and shadow lines when you see these different types of horizontal siding. Vertical siding, and as soon as it loads here, now we're starting to get into stucco and masonry and concrete-based siding. So used a little bit less often around here. But this is really good to go through and see some illustrations. And this is a great illustration of what gets insulated in a house. So if we're living in this space right here, and this space, I want you to notice that the insulation starting from the ground, and by the way, there should be insulation here on the inside and underneath this slab as well, and here on the inside. So if we did have that, our continuous insulation would go around the entire space that the humans are living in, all the way around back to the start point. Now, if we didn't want to have exposed ceiling here, or rafters here rather, and just put a ceiling across, then our insulation would follow that same path and then go across where the ceiling is and then down, and that would be an uninsulated attic space. But this is a good way to see how insulation, we want to think about where we're putting it, has to wrap around the spaces that we're going to be living in and heating. And these pages are going to be very useful to you for the homework that goes along with this, because I want you to be able to determine a rough estimate of what the R value of a wall system or roof system or floor system might be by understanding the R values of your materials and the R values of some insulation. So this illustrates what's going on and how do we come up with those R values based off of where we're kind of cutting through the wall. So if we have a wall with an empty cavity, the R value is pretty low because it's only adding up the R value of this gypsum wall board plus the plywood. If we're cutting through that same wall and we put a bunch of insulation inside that cavity, the R value bumps up to 31.7, depending on the type of insulation that we use. When we cut right through the stud without putting any insulation on the outside, that R value drops again. So we're going to look at that and see the performance basically of a wall system based on these R values. But let's back up a little bit. So first of all, we need to know some information about what is required in our area for energy code requirements. So energy code requirements are gathered from our IRC International Residential Code of 2016 I used as a reference. And what I wanted to show you here is if you looked under Maine, and look for our county, we are in zone 6A. That's important. That's key to know that number, number and letter system in this case, because this is going to tell us what our rules are going forward through the IRC. A little further into the section 11, which is the section 11 is the energy code requirements in IRC. So you can see this is table N1101.7.2, and this shows us that in zone 6 we have a heating degree day of 7,200 and no more than 9,000 is our range, if you will. The other piece here is just in metric units, so I just took the imperial ones. In delta T, remember, is the change in temperature we have from inside to outside that's giving us this value for our heating degree days over the course of the year. So an example here is if in the summer it's a 0, in the winter 0 delta T, but in the winter if I have an outside degree temperature of -5 degrees, then that means that I have a change, or delta T, change in temperature of 70 degrees difference from the inside comfortable degree of 65 to the outside temperature of -5. That's a difference of 70 degrees. And that means I need to use a lot of heat to do that. We get into looking at, the standards that we need to have for our windows and doors. Windows and doors are not usually given R values, they're given U factors. So I describe here the difference between a U factor and an R value. U factors are usually associated with assembled units, and they are measuring the transmittance of heat rather than the resistance. And then the reciprocal of the U factor is an R value. So we want the lowest U factor as possible, and we want the highest R value as possible. And the R value is measuring the thermal resistance of a material. So we want that to be as high as possible. And these are some numbers and equations that are important to know. We can add up R values, which is good. We cannot add up U factors. But our U factors are what's probably going to be noted in our manufacturer's specifications for our windows and doors. And that information has to be indicated in their manufacturer's specs to show that they meet code. Now, this is where all the meat and potatoes are for understanding thermal protection, if you will, for our climate. In climate 6, our fenestration, which is all of our windows, needs to have a minimum U factor of 0.3. And then our skylights, if we have skylights, 0.5, are glazed, fenestration, no rating. And then ceiling, R value needs to be 49. That's pretty big. That's where most of our heat is being lost, is in the ceiling. And this ceiling R value is only the ceilings that are exposed to the outside. So if I have 2 stories, the ceiling between my first floor and second floor does not need an R value 49, because that's inside our envelope of insulation. But the ceiling above that floor, if I only have 2 floors, on the ceiling between the second floor and the attic, that needs to be an R 49. Wood frame wall R values, 20 is indicative of what the R value for the insulation we're using has to be in the cavities. +5, there's a little H here that explains, I have another screen capture that explains what that H means, but I'll tell you, 5 R value for insulation that's either on the inside or the outside of the wall. That is continuous insulation. So this might be something like rigid insulation or insulation that's built into a panel. The mass R value is 1520, which means the R value of the cavity is 20. The performance of the wall cannot be less than 15. And we'll explain the performance of the wall here in a minute. Floor R value has to be 30, and the floor, again, is only the floor that is exposed either to the ground or to the outside. Basement wall R value is 1519, so 15 performance, 19 in the cavity, so 15 can be outside or inside R value, 19 can be in a cavity if we have a foundation system that has the ability to put insulation inside, which is not very common. And then our slab needs to be 4 feet below our finish grade to reach frost level, and it has to have an R value of 10 protecting it. And then our cross spaces have an R value the same as our basement, which makes sense, okay? So if we look at the next thing, this H is explaining that the R value is in the cavity insulation. The second R value is continuous insulation. Therefore, as an example of 13 plus 5 means R13 cavity insulation plus R5 continuous insulation. And that R5 continuous insulation can be put either on the inside or the outside of the wall. So there's a lot to it, but I really just want all of you to kind of have an understanding. So if somebody's talking to you about R values or U factors, you're not going to be like, what's that? So loosely interpreted, we need R49 in our ceilings. We need R20 in the cavities of our walls. We need about an R15 inside or outside in our basements. We need an R19 for our uninsulated spaces, floors above uninsulated spaces, or R10 with within our slab, with the slab at 4 feet below the frost depth. So does this traditional wall construction and floor construction meet the cut? And by the way, this is the cavity that's being referred to here in the box sill. So this floor system, notice there's no insulation between levels. This is first floor, this is second floor, but we want to fill insulation into this box sill cavity. Otherwise, we'd have just an open cavity with lots of cold air being able to come in. So if in this section view, we have the layers, 1/2-inch gypsum wallboard. We have insulation in the cavity that's 5.5 inches deep. That's the 2x6 is an actual 5.5 inches. And then we have a 1/2 inch of plywood, and then we have our approximately 1/2 inch siding. So that's the layers that we have in our wall system. Let's see what it gives us. So with this configuration, our R values going from inside to outside, starting with a 1/2 inch gypsum wallboard, is 0.45. And we can find that by going into our RValues. There's one reference there, but in our book, I meant to go to the book, the R values that we have here for building materials is where I'm getting that information. So our gypsum wallboard, which is gypsum right here, 1/2 inch is 0.45 R value. I'm using batt insulation first because this is the old insulation we used to use in the 70s and 80s. And really, I have to think of it as what's the best case scenario is in the cavities between the two studs. I have 18.15 R value. But wherever there's a stud, the R value goes down to 6.875. And if I have studs spaced at 16 inches on center, this R value represents 75% of the wall. This R value represents 25% of the wall. So if you do a little bit of math, you can figure out the actual performance is 15. And then we have a layer of plywood, which is about 0.62 R value, and a layer of siding, which is about 0.61. They're just about the same. So our total is 17.01 for an R value, and it doesn't meet our requirements because notice that the cavity is not at 20 R20. So that's a problem. We can't do this kind of construction anymore, basically. Okay, so what we can do, if we look at the next slide, there's some subtle differences. First of all, I increase the spacing between the studs, so that's giving me more space for insulation rather than studs. And I'm also replacing the insulation on the inside with blown-in cellulose, which has got a much higher R value per inch than the batt insulation. So we go back to our R values. Whoops, I keep clicking the wrong thing here. And we look at the second page in your book. The batt or blanket insulation, which is that pink stuff that got used in the 80s, is only 3.3 inches R value per inch. If we put in the blown-in cellulose, it's 3.7, which doesn't seem like a big difference, but it does make a big difference when we look at the difference in R value we're able to get in the wall. And I think there's even better numbers that you can get now with dense packed cellulose. So this is just very conservative that I'm using from the book. So we've replaced that. So now we do have a cavity of 20, at least 20. And because we've changed our stud spacing to 24 inches on instead of 16, we can now associate the 20.35 with 85% of the wall. And this stud is now worth 15% of the wall. So now our performance for our wall is 18.33, which is pretty good. And then when we add up all of our R values, we actually end up with a 20 R value total throughout the whole wall. So that is at least a slightly better solution. Now, we could get even better with this as soon as we start to put that layer of continuous insulation on the outside and push all of these things out a little bit, and maybe even add 1 inch of rigid insulation. It makes a huge difference in the wall performance. So if we were to do the same thing with ceiling R values, so let's just take this ceiling right here. From the inside to the outside, we have 1/2 inch gypsum wallboard here. We have, I'm just going to call it an airspace because it's where the strapping is. So it's about 1.01 for airspace. And airspace does show up here as part of your, if you look at airspace, 3/4 of an inch, it's non-reflective, 1.01. And then we have 2 layers of 6-inch batt insulation. That's kind of an older way of insulating, which would add up to 39.60 at 75% of the ceiling. Because again, our ceiling joists are spaced at like 16 inches on center. So where the ceiling joists are, we're only getting 6 inches of insulation and then another 6 inches on top of that. So it's down to 39. I'm sorry, at the cavities, it's exactly 39.60, where we've got insulation, 2 layers of it in the cavities between the ceiling joists. But where there is a ceiling joist, we're only getting, we're getting a ceiling joist, then we're getting 6 inches of insulation. So it goes down to these 2 numbers put together. So our combined performance is 34.24 for the ceiling, which is wholly inadequate, because we're now required to have an R value of 49 in the ceiling. So how do we fix that? We have to put in some blown in insulation up here, 24 inches deep, in fact, and that will more than do it. And that will bring our R values up to 78, which that's a good number to get for your ceiling. So this is what a more modern cross-section would look like, and I actually did this with the Josephine. So this is a pretty typical way that you might show blown-in cellulose insulation. And what we have here is what's called a proper vent, or a baffle that keeps the insulation from going up right up against the underside of the roof. So we have some air space here blowing in and around and above the cellulose. So this has got to achieve about 24 inches deep of cellulose, and we'll end up achieving that 78 R value here. Also inside the wall, instead of using the batt insulation, we're going to put in dense packed cellulose. And then in here, in the box sill cavity, we'll make improvements by filling those areas with foamed in insulation. And then you can see at the bottom here, we have rigid insulation that's going from the right from the slab all the way up to the underside of that foamed in insulation. So now we're creating a much more continuous barrier of insulation that's a much higher performer insulation for our wall system. And so it's creating a better building science for a more efficient home. So your homework is from the lesson plan that we have for this week. If we look at our lesson plans, there's 2 things. One is to pick out floor joist size for floor joists in the Josephine. So let's take a look. So you can go ahead and use the Josephine dimensions to pick out those floor sizes, roof rafter sizes. In the previous video, I show you how to pick out roof rafter size as opposed to a floor It's pretty much the same thing. You can use the same tools. So here you're using the Josephine to come up with your what's your maximum roof span, what's the depth and spacing of the rafter, and then what size ceiling joist do you need to have. And this will be based off of where you put your interior walls, so choose wisely. And then the second part is I'd like you to tell me what the R values would be for these layers, and then come up with what is the R value just at where the insulation is. So I don't need you to work out what the performance of the wall is, but what's the R value of the entire wall system if you're cutting through from gypsum wallboard all the way to the other side, going through the insulated part of the wall. What would it end up being? And then you're going to be adding or sketching a roof cornice detail at the 1 inch equals a foot scale. And it can be added to your wall section or can be drawn on its own, and that will be added to your set of drawings. So that last page right here, this is a pretty good example of what that cornice detail might look like, but it would be better if we could blow that up and really call out what's going on here in the roof. And you'll see all that by looking at that previous roof lecture. Shows you pretty good information about what would be in there for construction. So that sums up what we're doing for this week. You got roofs and R values. And I'll see you Tuesday and Thursday this week. Thank you.